everything you heard so far about 3D printing is not 3D. So today I will talk about the first real 3D printing process. I will show the relation from a fat man to a human hair. I will take you for a sightseeing trip, and I want to tell you about curiosity that led to the world's peak record in nanoprinting. But first of all, why do I claim that all printers so far are not 3D? Well, you have seen these 3D parts. Obviously, they are 3D. But what do you do in conventional 3D printing is you create a CAD model. You can apply any color you like to it. Then you create a three-dimensional mesh. You put it in your fabrication machine, just like the machines you have seen out there, the solid doodle. And then the part is created layer by layer. And this layer by layer approach is not really three-dimensional. It's 2.5 dimensional. It's just like building in a house, putting bricks on top of each other. But today I want to talk about a different technology. It's always technological people that make technological problems. So a real 3D process would be like this. We create a solid part here, a solid part there, everywhere we would like, just like seen on this, you can see on this little video here. And what we get in the end is some part that is similar to the first one, but we create it really three-dimensional, so we can just apply a solid part here, solid part there, everywhere we like. And this technology is called two-photon polymerization. And the heart of this technology is a femtosecond pulsed laser. This laser emits in the near infrared region, so this is light that you actually can't see. And this does not do this continuously. It does it in pulses. And these pulses, they are very, very, very short. So it switches on and off very fast. And one pulse is just several femtoseconds long. Maybe you know milliseconds. Today there is Formula 1 race. Formula 1 laps are measured in milliseconds. But then a millisecond is 1/1000th of a second. And 1 microsecond, this is the smaller unit, is 1/1000th of a millisecond. And then so forth, we've got nanoseconds, picoseconds, and then femtoseconds. So femtosecond is 10 by the power of -15 seconds. And what does this actually mean? Well, if we put a relation from 1 femtosecond to 1 hour, that would be the same relation of 1 hour to 114 billion years. That's about 8 times the age of the universe. You know that the speed of light is the fastest that we know. From here to the moon, the light only needs 1 second. And in 1 femtosecond, the light is only able to travel 300 nanometers. 300 nanometers is about the length of this papillae of the lotus leaf that provide this famous hydrophobic self-cleaning effect. So in other words, 1 femtosecond is 0.0000000000000000001 second. But how is this actually related to 3D printing? If we mirror this laser, the laser beam, into a photoresist, if we focus this into a substance that can cure under the influence of light by some quantum mechanical effect that you shouldn't bother about, it's just like Wolfie said before, he is linking data, we are linking material components, and so we create these three-dimensional polymeric lines just by turning a mirror in front of a focusing objective, in this case, microscope objective. So we can create structures like this fat man here, which consists of about 1,000 or millions of these small units, of these small polymeric lines. And you've probably noticed the scale bar below this fat man. It's only 20 microns. And just in relation, a human hair is 60 microns thick. So we can actually put this man on a human hair. Of course, this is just a Photoshop illustration. He always tripped over because he was too fat. We actually tried it to fabricate on the structure, but we didn't make it. What else can we do? Well, we can do nano-sightseeing in a scale from 1 to 1 million. The good thing about nano-sightseeing is that the Earth's circumference is only 40 meters in a scale from 1 to 1 million. So to London, this is only 1.2 meters. The only thing you need to have is a scanning electron microscope to observe this tower bridge in full details from the outside, from a bird's perspective. Or you don't even have to look so far. 1.8 millimeters away, the St. Stephen's Cathedral. And you can observe St. Stephen's Cathedral the first time without any construction scaffolds. And lately, we had some visitors at St. Stephen's Cathedral. Some human cells, they call themselves chondrocytes, were observing the roof of St. Stephen's Cathedral, and they were also very impressed by a Gothic building. But this technology is not new. We have experience since 10 years now on creating these microstructures. The first theoretical description of this process was done in the 1930s. The first experimental proof was in the 60s, and since the 80s we have the first application, mainly in microscopy or tweezering, and since 2000 we have two-photon polymerization. So last year Klaus Stadelmann was talking about two-photon polymerization, and he presented this as his usual working field. He said that he went to the lab one time and he couldn't fix the problem, the laser was broken, and at the time I was his diploma student, so I had the problem too. But still, for me, the process itself, two-photon polymerization, I was very curious about. So I studied every detail of the device, of the two-photon polymerization machine. I tried to understand every principle. And together with my colleague Peter Gruber, we managed to improve this machine. We improved it the way that we now can build up polymeric construct at the threefold increase of speed. And this is the only way how the process ever can get into industrial applications, because we are writing really with a very thin polymeric line. So this is a three-dimensional pen. And if you want to create structures in 3 dimensions, with this detail, you need to go very fast to get a structure. And this was shown with this little race car here. In the slow motion, you can actually see how one polymeric line is created and how fast it goes in real time. The whole car consists of about 10 meters of polymeric line, though it's only 313 micrometers in length and 80 micrometers in width, and about 100 micrometers in height. So we really improved the inertia, we improved the chemistry on this process, and we really got a step towards an application, a real application for this technology, which so far wasn't the case, as you probably would reckon. So after 4 minutes, conventionally the fabrication of this race car took about hours or even days. And we've got this race car in just 4 minutes. At the end of the process, you can see cross-sections of the car. And in the scanning electron microscope, you see the outcome, really in accordance to a CAD model. This can be never done with any other technology. So this has a real repeatability of below 1 micron. So I have a personal question for you now. Do you need this? Do you need cars that can park in your blood vessels? Do you need to watch fat men in the microscope if you can go on the street? Do you need human cells visiting St. Stephen's Cathedral? Well, obviously not. But still, the race car that can't move but still breaks the speed record went around the world. And a lot of people were very curious about it, not only me. So I'm curious about the femtosecond, about that we can create these fast switching pulses. I'm curious about the first real 3D printing process. And I'm curious that we can create structures that we could never create before. You might argue, okay, nerd. Yes, okay, I am one. I don't care. At least I'm one of the 20% that's fond of his job. And but actually, there must be some nerd in all of us. Like the whole world was interesting in this race car. But of course, I don't want to waste the tax money. So this is not a toy that's just for the sake of mad scientists that are playing with it. So I will talk about applications now. There are three major applications that you can use it for. So research is going in 3 directions. The first one is optoelectronics. So you can actually link electronic devices in a 3-dimensional manner. And as you've heard, these wiring techniques is really precise. So this can be a good technique for the fabrication of next generation microchips. The second one is surface modification. In surface modification, we can, like I showed the lotus leaf already before, you can potentially create this fine papillae. And with this fine papillae, you can provide the same effect on every surface. So it's self-cleaning, hydrophobic. You potentially don't need to clean your TV anymore. And on the other hand, with surface modification, we can also do very adhesive structures. We can provide little hooks that can stick like the gecko and still provide the self-cleaning effect. So this is another very tremendous application. And the third one, which we are mainly focusing on the third one, this is tissue engineering. In tissue engineering, you usually get cells from a biopsy, you transplant them on a polymeric scaffold. This polymeric scaffold we are producing with 2-photon polymerization. Then you create a graft, and this graft is then transplanted in the patient again. So we can create artificial organs. And with this technique, it was already proven that you can create skin, liver, kidney, blood vessels, and lately there was some publication also about neurons. So you can actually create guides for neurons, which would be a really nice tool to have. And there's another application, and I was talking about the near-infrared laser. And as any one of you might notice, or might know, when you shine with a flash lamp through the hand, it appears to be red on the other side. And this is not because the blood is shining or something like this. This is because the red share of the light is penetrating the tissue. And the near-infrared light does this also. So the blue and the green part is absorbed, and the near-infrared light penetrates through. What does this mean to tissue engineering? Well, we can probably construct these little scaffolds inside the body without cutting the patient open, and without any scars, higher chances of curing, shorter recovery phases, and repeatedly treatments. So this is really very nice, especially for the people that have cartilage problems, because cartilage cannot regenerate by itself. So, but I'm certainly sure this is a very new technique. I'm certainly sure that these are not the only applications for it. So I want to share my curiosity with you. I want to push it to you, and probably you are creative Like Georg was creative with the QR codes. He finally found an application for them. So be creative. We can provide a lot of functions at the scale relevant to the human when we can construct in these fine details at 100 nanometers. So I want to end my talk pretty early. I want to end my talk with the words of Richard Feynman in 1956, opening the way towards nanotechnology. There's plenty of room at the bottom, so be creative.